So what we're going to go over today is the basic rules for differentiation without having to do the limits, okay? So I'm going to say this today, all right? You're going to take a test where you have to do find the derivative using the limit process, okay? So these are going to start being shortcuts so we don't have to do that limit process. But on that next test, you may not use any of these rules other than to check your work to see if you did it right, okay? So this is really going to speed things up so we don't have to do those limit statements, okay? So some notation that we need to realize that we're going to use a lot of in the next months or so, okay, is f of x, all right? The derivative of f of x, we would write f prime of x. Nothing new. You've already seen this before, okay? If it's y, then we're going to write dy over dx, all right? And I want you to get used to both notations. You got to understand both of them, okay? All right, so here we go. First rule, all right? The derivative of a constant is, okay? And so a constant is a horizontal line, which would mean, right? Which would mean that the derivative would have to be 0 because derivative is the slope at every point, okay? So the derivative of a constant is 0, okay? So the way we'd write that in this notation is d dx, and c represents some constant, okay? Then this would equal 0. So what we're going to see is something like this. The derivative with respect to x of some number like -7, okay? And we know that that comes out to be 0. So this has to be a number. That's what the c represents, is some constant, some number, all right? Okay. Now, the next, it's so much better in class when I'm with you guys, because I want you to look for a pattern. I'm just going to start giving them to you, and I want you to see what the heck, how am I going from the function to the rule, okay? So to the derivative, like what is it that I'm doing, okay? Okay, so f of x is equal to x squared. The derivative of that, f prime of x, okay, and I'm wanting you to try to figure out what the heck I'm doing. Okay, so f prime of x is equal to x squared, or sorry, f of x is equal to x squared, so f prime of x would equal 2 times x to the first power. And we probably wouldn't write first power, we just write 2x. If f of x is x to the fifth, f prime of x is going to wind up always being 5x to the fourth. If f of x is equal to x to the seventh, then f prime of x, the derivative, is 7x to the sixth power. Hopefully you're kind of picking up on, hey, wait, he's just doing this, all right? Hopefully you see that. So if f of x is equal to 3x squared, okay, I'm going to tell you something. This is actually two rules at once, okay? So f prime of x would equal 3 times 2x to the first, which would actually give you just 6x. And that would be the derivative, I can't say it, the derivative of 3x squared is 6x. And it's that fast, okay? It's like, why didn't you show us this earlier, okay? So do you guys notice what's happening, all right? So if I take x to any power, how are we getting these out of there, okay? And usually I try to pull it out of you guys and you guys see it and somebody says, hey, you're just doing this. So I can't tell right now if that's happening or not, but hopefully you realize that if I have to take the derivative with respect to x of x to the n, all I'm doing on all of these is I'm bringing down the power, so it's going to be n times x. And what am I doing to the power? I'm getting a new power, right? But what am I doing? I'm subtracting 1. So it's going to be n, which was the power, minus 1. That's going to be the new power. And that's the rule. It's called the power rule for derivatives. All right. So let me do some examples here. A lot of times we're going to have to rewrite them before we can actually apply this power rule. So we've got to make it look like this: x raised to a power. That is our job. We got to make it look like that. Okay. So here we go. We got to write it as x to a power. And this is coming to us written in that form. So we don't need to change anything for this one, right? So f prime of x for this would simply be 3, because I'm bringing that power down, times x raised to the 3 minus 1 power, which would actually be the second power. Okay, so the derivative of x cubed is 3x squared. Okay, so this next one is not written as x to a power, but we can write it as x to a power because we have to realize that really roots are actually fractional exponents. So this could be rewritten as x raised to the 1/3 power because the cube root is equivalent to 1/3 power. All right. So now be careful because now g of x, right? We've changed the function name. So don't always assume it's f and always write f prime. This is actually going to be g prime of x. So g prime of x is equal to, and it's the same rule, okay? We take this power of 1/3 and we bring it down, all right? So 1/3 x to the, and we're going to take this power, I'm actually going to write it all out this time, 1/3 minus 1, right? But subtracting 1 is the same as subtracting 3/3 because 3/3 is 1. And that just automatically gives us a common denominator so that we can subtract. All right, so this means g prime of x would equal 1/3 x to the negative 2/3 power. And x to the negative 2/3 power, okay, I want you to write this without negative exponents, okay? So then that means g prime of x would equal 1/3 times 1 over x to the 2/3 power. And so that means g prime of x would equal 1 over 3x to the 2/3 power. And that's what the answer is to this. Okay, so for this next one, y equals 1 over x squared. Okay, so we need it so it's x to a power. It's not written as x to a power, but we can still write it as x to a power because we could rewrite this as x to the negative 2 power. So now, because it's y, we're going to switch and use a different notation. So the derivative of y with respect to x is dy over dx. Okay, and now we're going to bring our power down. So this is negative 2x to the, and we're going to take 1 away from this. So negative 2, take 1 away, actually becomes negative 3. So then cleaning this up, that makes dy over dx equal to negative 2 times 1 over x to the 3rd power, because I want to write this so it doesn't have negative exponents. And then dy over dx simply becomes negative 2 over x cubed. And that's the answer to these, okay? So let's look at some more, what can we do if something else happens, all right? And that's what the next thing is. So a lot of times we don't have just x to a power, we have x to a power times some number, okay? And what we can do is use what's called the constant multiple rule. So if you have and this works for any function that you're taking the derivative of, if you take the derivative of some function, which in this case is going to be x to a power, times some constant, then that's always going to be c times, and then just the derivative of the function part, f prime of x. So what does that mean for this? Okay, so y equals 2 over x. We would need to rewrite this as 2 times 1 over x, which becomes 2 times x to the negative 1. So here we have x to a power, but we're multiplying it by a constant. All right, so that's where we need to use the power rule along with this. So that means when we take the derivative of y, because it's written in y form, so I'm going to write dy over dx. That's always going to be this constant, which happens to be 2 in this case, times, and then now we're going to do the power rule for x. So it's going to be times negative 1 x to the negative 2 power. So that becomes negative 2 times 1 over x squared, or this becomes negative 2 over x squared. And that's the derivative of 2 over x. This one right here needs to be rewritten as 5 halves times 1 over x cubed, which really could be rewritten as 5 halves times x to the negative 3 power. So now my constant happens, it's still a constant, but it happens to be a fraction. So dy over dx becomes the constant, 5 halves, times negative 3, because I'm bringing my power down, that's how I'm getting the negative 3, x to the, and I'm going to take 1 away from this power, so negative 4. And so this constant now becomes negative 15 halves. So dy over dx is equal to negative 15 halves and times, and then x to the negative 4th becomes 1 over x to the 4th. And so our final answer would be written as dy over dx is equal to negative 15 over 2x to the 4th. And that would be our answer to this. Okay, let's do a couple more. So for this next problem, okay, f of t is equal to 5 over 2t in parentheses, right? The 2t is in parentheses raised to the 3rd power. This is not x to a power or t to a power. It's 2 times, all right? So we cannot apply the power rule to this. It will not work. So what can we do instead? Well, we need to apply exponent rules. So this is equivalent to 5 over, and what is 2t raised to the 3rd power? Well, it's 2 to the 3rd times t to the 3rd. That's our exponent rule that we're going to use. So this becomes 5/8 times 1 over t to the 3rd power, because 2 cubed is 8. And then we're still going to write this. So f of t becomes 5/8 times, and now we can rewrite this part as t to the negative 3 power. And now we're ready to take the derivative because we have a constant times a variable raised to a power. All right? So f prime of t becomes 5/8, because that's my constant, times negative 3t raised to the, and then what we're going to have to do is just take 1 away from this, so it becomes negative 4. So that makes f prime of t equal to negative 15/8 times, and this t to the negative 4 becomes 1 over t to the 4th. So our final answer would be written as f prime of t is equal to negative 15 over 8 t to the 4th. And if you had the negative up with the 15, that'd be fine. No big deal. All right, this next one is y equals 1 over 2 times the cube root of x to the 5th. So this could be rewritten as 1 over 2 times x to the, and this, the cube root of x to the 5th could be rewritten as x to the 5/3 power. So 5 over 3 power. We could separate this so it becomes 1/2 times 1 over x to the 5/3. And because we don't have a, so right now all we can do is a variable raised to a power, or a constant times a variable to a power. And we don't have a constant times a variable to a power. We have a constant times 1 over a variable to a power. But we could rewrite this. So y winds up being equal to 1/2 times x to the negative 5/3 power. Now we have a constant times x to a power, and we can take the derivative of it. So dy over dx is equal to, so this constant, which is 1/2, times, okay, so we're going to bring the power down, so that we're going to multiply by negative 5/3, and then times x to the, and then we had negative 5/3, and we want to subtract 1, but the version of 1 that we want is minus 3/3. So that makes dy over dx equal to negative 5/6 x to the negative 8/3 power. But then x to the negative 8/3 power could be rewritten. So that means dy over dx is equal to negative 5/6 times 1 over x to the 8/3 power. And so dy over dx is equal to negative 5 over 6 x to the 8/3 power. Okay, and you don't need to convert this back to radicals, to the roots. Just leave it as 8/3 power. Okay. All right, let's go to what happens if we start adding these together, okay, or subtracting, x to a power, because that's a polynomial, right? How do you take the derivative of a polynomial? So that's what's next. So for this next one, this is called the sum and difference rule. All right, so we have the power rule, we have the constant multiple rule, now we have the sum and difference rule. So if you take the derivative with respect to x of f of x plus or minus, so that'd be the plus would be the sum and the minus would be the subtraction one, okay, or the difference. Then if you take the derivative of when you add or subtract things, then you just take the derivative of each one. So f prime of x plus or minus g prime of x. Okay, I want to say something that's going to be coming up, all right? And I want to make sure I'm going to say it a million times so you don't make this mistake. When this becomes a product, it is not the same as this, okay? It's not like you can just take the derivative of each one and multiply the results together. And I will show you later on that just doesn't work, okay? There's another rule for when it's a product, okay? All right, so how do we find the derivative of f of x equals x cubed minus 4x plus 5? Well, this is just x to a power. This is a constant times x to a power. And then this is just a constant, right? And I'm adding and subtracting in between. So all I need to do is take the derivative of each one individually, okay? So this is f prime of x would equal, okay, so we just got to worry about how do you find the derivative of x cubed? Well, that would be 3 times x squared. Okay, now I know this is subtraction, but we can treat this as being like a -4, okay? So this would be -4, so minus 4 times, okay, and that's my constant. The power here is a 1 right now, right? So if I bring it down, that means I'm going to multiply by 1, and I'm still going to have x, but I'm going to raise it to the 1 minus 1 power, which actually becomes the 0 power, and then plus the derivative of 5, which is the derivative of a constant, which is 0. All right, so now what is x to the 0 power? Well, x to the 0 power is going to wind up being just the number 1. All right, so that means f prime of x is equal to 3x squared minus 4 times 1, which would just be 4. And that would be the derivative of f of x is equal to x cubed minus 4x plus 5. The derivative would be 3x squared minus 4. Okay, how about for this next one? Okay, so this next one, we need to rewrite it first. So we're dividing by 2, but dividing by 2 is, dividing by 2, but we have a negative, right? So that's the same as multiplying by -1/2. So g of x needs to be rewritten as -1/2 times x to the 4th plus 3x cubed minus 2x. So that would mean g prime of x would be -1/2, because that's my constant, times 4, because I'm bringing the power down, x to the 3rd power, plus this constant 3 times 3, and that's just bringing this power down. So that's this 3 right here is that power right there, times x to the 2nd power minus 2, and then this is a power of 1, so that's going to be x to the 0 power. Now, hopefully you realize when it's x to the 0 power, we can ignore it and just write a 1 there, okay? So that makes, cleaning this up, g prime of x is equal to, well, what's negative 1/2 of 4? Well, it'd be negative 2. So this is negative 2 x to the 3rd power plus 9, because 3 times 3 is 9, x squared, and then minus 2 times 1, which is just minus 2. And that's the derivative of g. All right, let's go to this next problem. So on this problem, we want to find the slope of the tangent to the graph of f of x is equal to x times the quantity x minus 4 squared at the point 624. So let me make this really clear to you. They're just asking for the slope, not the equation of the tangent. So just the slope. That's what that on the last quiz, that's the mistake that we made, is like you guys were trying to write the equation of the tangent line. That's not what it was asking. It was just asking for the slope. Okay, so pay attention. This just is asking for the slope at this particular point. Okay, so how can we do that? Well, we don't know how to take the derivative of that. We know how to take the derivative of x to a power. We know how to take the derivative if it's a constant times x to a power. And we also know how to take the derivative if it's a constant times x to a power and you're adding the same, the same things, another number times x to a different power and so on. So how are we going to do this? Well, what you have to realize is that what your options are right now is to just multiply this out and use algebra, because if I multiply it out, I'm going to get a polynomial. All right. So f of x is equal to x times x minus 4 squared. That's what we're starting with. We can't multiply this yet because we'd have to use exponents first. So that means I need to square this. So f of x becomes x times, and then squaring this gives us x squared minus 8x plus 16. And because I've squared it, I can now distribute the x. So f of x is x cubed minus 8x squared plus 16x. Okay, now because we've rewritten this, now we can find the derivative. So that means f prime of x would be 3x squared minus 8 times 2x to the first plus 16x to the 0, but x to the 0 is 1, so I'm not going to write it, okay? I'm sorry, x to the 0 is not 0. X to the 0 is 1, all right? I think I said that, all right? So x to the 0 is 1, and that's why I'm not going to write x to the 0. Sorry about that. All right, so f prime of x cleaned up becomes 3x squared minus 16x plus 16. And so what we needed the derivative in order to find the slope of the tangent, but that's all we need, slope of the tangent. That's it. That is it, okay? So f prime of 6 is equal to 3 times 6 squared minus 16 times 6 and then plus 16. Okay, so that means f prime of 6, the derivative at 6 would be 3 times 36 minus 16 times 6 plus 16. So that makes f prime of x equal to 3 times 36 is 108 minus 96 plus the 16. And so f prime of 6, the slope of the tangent at the point 624, the slope would wind up being 108 minus 96. So that'd be 12. And then plus 16, which gives you 28. So the slope would be 28 at the point 6 comma 24. The slope of the tangent is 28. All right, let's go and do some other problems, some more thinking problems, okay? So for this next problem, they're asking you, does the curve y equals x to the fourth minus 2x squared plus 2 have any horizontal tangents? If so, where? So how do you find a horizontal tangent? What's special about a horizontal tangent? Well, horizontal tangents have a slope that is 0, which means in this case, the derivative, which is dy over dx, would have to equal 0. So horizontal tangents means that dy over dx would have to equal 0. For this to happen, that has to be true. Okay, so here we have y equals x to the fourth minus 2x squared plus 2. That would mean dy over dx. And I'm going to start doing some stuff in my head now, okay? This one, the derivative of x to the fourth, would just be 4x cubed. Okay, and then we'd have a minus. And the derivative of 2x squared, well, I bring the power down, so that'd be minus 4x, right, to the first, which we don't need to write first power. And then plus the derivative of 2, which would just wind up being 0, so I'm not going to write it. Okay, so I need to figure out what x's cause this to come out to be 0. Because if this were to come out to be 0, if there's an x that causes dy over dx to be 0, that would mean we have a horizontal tangent. So we're going to set this equal to 0. And then we're going to factor this. Now there's a GCF here of 4x. So I'm going to factor out a 4x. And I'd be left with x squared minus 1. And you should recognize that's a difference of squares. So that means 0 is equal to 4x times x minus 1 times x plus 1. And the only way for this to be 0 is if this factor is 0, this factor is 0, or this factor is 0. The only way for this factor to be 0 is if this x is itself 0. So our answers are x equals 0, x equals 1, and x equals -1. Okay, now this is not function notation, right? So we can't write, some people will write like y of 0, like it's a function. And you could, all right, people do that, but I'm going to show you an alternative to doing that, okay? We're going to find y at, and a vertical line like that means at, and then we write x equals 0. And so that would be 0 to the fourth. Everywhere I see x in my function, I'm going to put 0. So 0 to the fourth minus 2 times 0 squared plus 2. Well, that would come out to be 2. And then I'm going to also do it when for y at x equals 1. And this is just a notation that we use in calculus to say, hey, we're putting x equals 1 into the y and figuring out y. So this would be 1 to the fourth minus 2 times 1 squared plus 2. So this would be 1. This would be 1 times -2, so that's minus 2, and then plus 2. And so that comes out to be 1. And then we also need to do y at x equals -1. So that'd be -1 to the fourth minus 2 times -1 squared plus 2. Well, -1 to the fourth, that's going to be even number of -1, so it's just going to be +1. And -1 squared is 1 times -2, so -2, and then plus 2. Well, this one also comes out to be 1, right? All right, so these are the points where the graph of y equals x to the fourth minus 2x squared plus 2 has horizontal tangents, okay? So y equals x to the fourth minus 2x squared plus 2 has horizontal tangents at the point 0, 2, comma, 1, 1, comma, and -1, comma 1. Because all of those x's, okay, wind up causing the derivative to be 0, all right? And those, when we put those x's in, okay, we also get a value for the y. Now, this can happen, so I'm going to start you early on this, okay? You can have an x value for a derivative that winds up causing it to be 0, but if the function itself might be undefined at that x value, which means there's no horizontal tangent there, okay? So that can happen, all right? So there's two things here. We figured out where the derivative was 0. These are the x values that causes the derivative to be 0, but we also have to check, do these x values actually exist on the function? And they do, all right? In this case, they do, because we're not being too technical right now, but I just want you to understand that, okay? All right, the next problem is probably the hardest type of problem that I could give you at this point in calculus, all right? So we gotta put your thinking caps on, hang in there, and figure this out. So this next problem is probably the hardest problem that I can give you right now. Technically, it's not that hard, all right? The algebra is not hard on this, but it really requires us to understand the role of what it means to be tangent to a graph, okay? So I'm gonna draw a picture first to help us understand. So here we have a function, right? This is f of x. So y equals f of x. And then I'm gonna use a different color even. So let me grab a different colored pen. All right, and then this right here, let's say that's the tangent line, okay? So if that's the tangent line, this would be the point right here. This could have, the tangent line could have an equation like this. It's a line, so it's y equals mx plus b, okay? And then we know that this line and this curve share this point where they touch. That's called the point of tangency. Let me slide it down a little bit. This is the point of tangency. And they both have, at that point, they both have the same x and the same y coordinate. All right. Now, this m right here is the slope. It would be the derivative of f at whatever this x value is. Okay. And so because we know find the k such that y equals k plus 4 is tangent to the graph, that's our tangent line, okay? So right here, what this is telling me is y equals 1x plus 4, and at the point of tangency, dy over dx, the derivative has to equal 1. Has to. We don't know the x that it happens at, right? But we know this derivative has to come out to be 1. If for this k to exist, the derivative has to come out to be 1. Okay, the slope has to be 1. All right, so let's start with this. Okay, now k is going to be some constant. It's some number. We just haven't figured out what the number is yet. So we know f of x is equal to k times, and we need to rewrite this so it's x to a power, so the square root is just a 1/2 exponent. So this is k times x to the 1/2. Okay, so what I'm going to do is I'm going to go about finding the slope of this, or finding the derivative of this. So that means f prime of x is equal to, okay, so this is a number, so this is a constant, this k, so it's going to be k times, and then 1/2 x to the negative 1/2. Because how do we get the negative 1/2? Well, we took 1/2 and we subtracted 1. or we subtracted 2 halves. And 1/2 minus 2 halves is -1/2. So that makes f prime of x equal to k over 2, right? K times 1/2 is k over 2 times 1 over x to the 1/2 power. So that means my derivative f prime of x is equal to k over 2x to the 1/2 power. Now, I don't know where this is, where I know the x value, where this happens is the point of tangency, and I know the slope here is going to be 1. So f prime of some x value, which we haven't found yet, is going to have to be 1. So I'm going to set this equal to 1, which is equal to k over 2x to the 1/2. So let me explain this again. Okay, so I have the derivative. I know there's some x that I could put in here that the slope has to come out to be 1. That's why I put this 1 right here. Okay, so here's the problem. We have 2 unknowns. We don't know the x, and we don't know the k. All right. So what we're going to do is we're going to solve this for k and then plug that into this equation or into the function. So what this means is 2x to the 1/2 power must be the same as k. Okay, so what do I know about these two? Well, f of x is y, and here's why. Well, this point right here, they have to be the same exact y. So that means k square roots of x must equal x plus 4. Has to. Okay? At the point of tangency, let me write this in a different color. And this is what's allowing me to write this. At the point of tangency, the function must equal the tangent line. Because this y equals fx and y equals, right? We are doing, basically we're going to do substitution. Because I know, let me zoom out a little bit. Because I know this function and this tangent line, those 2 points, those 2 curves share this point. That's what I was trying to say. All right, so how's that going to help me? Okay, knowing that, because I still have 2 unknowns, right? And over here I have 2 unknowns. But now because I solved this for k, if we have 2 unknowns, we need 2 equations, and we have them, right? We got this k from doing the derivative, but over here we can replace this k with what k is equal to. We know k always has to equal 2x to the 1/2. So this becomes 2x to the 1/2 power times, well, the square root of x is also x to the 1/2 power, and then that has to equal x plus 4. So look what just happened. Now we just have an equation with just x in it, right? Because we did a substitution, okay? So x to the 1/2 times x to the 1/2, well, that's just x. So this becomes 2x is equal to x plus 4. Subtracting x from both sides, we get x is equal to 4. Okay, so you know what this tells us? This tells us what the x coordinate is for this point of tangency. It's at x equals 4. Where this is going to happen is at x equals 4. Now, I still got to find the k value, right? So in order, because that's all it's really asking you. It's not asking you for the full-blown, what's the point of tangency? It's asking for the k that would make this true, right? So if I take this and put it back over here, I would actually now have what the k value is, okay? So k is equal to 2 times 4 to the 1/2 power. Well, that's just 2 times the square root of 4, which is square root of 4 is 2. So 2 times 2 is 4. Our k is 4. Okay? And that's the answer to this problem. Okay? That's all we needed to know. All right, guys. Derivative rules. Day 1. Okay. We went from some really simple things to this is a harder problem to understand for a lot of students. So if you're like, what? I don't get that. Okay. It's going to come over several days. This will make more and more sense. Okay. All right, guys. That's it for today. Yeah, that's it. All right. Well, let's meet back on Zoom.